sorry about that. Just this couple of last 2 minutes. Okay, so we can calculate the exact area for, calculate the exact area using the limit of the Riemann sum for polynomial functions degree 1, 2, or 3. We are not equipped with any other knowledge. How come? How come that I cannot determine the limit of the Riemann sum for sine, cosine, tangent, etc., etc.? Here's why. Because that's all I know. I don't know the limit of sine. I don't know the sum of sine. I don't know the sum of cosine. That's all we know. Linear, quadratic, cubic. Now choose any function you like, any interval you like, and let's determine the exact area under the graph using the limit of the Riemann sum. Any function. Any interval. The calculations can get hairy, I have to warn you. If you don't want to choose, I will. Anyone? Anyone? Anyone would like to choose? Okay, I'm going to choose 2x squared plus x, let's say plus 4, and between 0 and 4. So you can see the technique. I also want to mention something about area. Let's suppose this is 0 and this is 4. It's not this function, but let's suppose I'm asked to find the area between 0 and 4 under this graph. Will this area be positive or negative? The answer is it will be negative, because this will be a positive area, but it is much smaller in my graph than this area. So the positive area and the negative area, and the answer will be negative. So don't get scared. Areas could be negative. Good. So we need 3 preps. So the question here is find the area under the graph of f of x between 0 and 4. And we need 3 preps. The first prep is delta x. What are all these preps? These are the preps. This, this, and then this. 1, 2, and 3. Once I have those, then I can put everything together and determine the area as the limit of the Riemann sum. Okay, so delta x by definition is 4 minus 0. I chose 0 because every time we start at 0, it would be much easier to calculate. So let's start with the first one with 0. Divided by n. So this is 4 over n. So we have delta x. Number 2. We have to determine xi. What is that? What is xi? So let's take a look at this interval between 0 and 4. Imagine the function is somewhere here. Okay, so I will divide this interval into n subintervals. each subinterval will have the same width. This is delta x, which is 4 over n, and so on and so forth, all of them. At some point in time, I will get to this point, which is, so if this is the leftmost point, this will be x1, this will be x2, this will be x3, this will be xi, this will be xi plus 1, and this will be the last one, x sub n. Because again, it doesn't matter. N will go to infinity, so if you consider the rightmost point, the leftmost point, or the midpoint, is not going to matter. Okay, so now obviously x sub 1 will be 0 equals 0 plus 1 delta x. X sub 2 will be 0 plus 2 delta x. 2, 4 divided by n. X sub 3 will be 0 plus 3, 4 over n. Can anyone give us x sub I? What will that equal to? Anyone? So that would be I, 0 plus I, 4 over n. In short, 4i over n. So this is our xi, 4i over n. If we didn't start at 0, if I had started, let's say, at 3, then xi would have been 3 plus 4i over n. But that's not our case. I started with a simpler example where the leftmost point of the interval is 0. The last prep before we look at the limit of the Riemann sum will be f of xi. No problem. I have to plug in 4i over n in this function. Not a big deal. So this is 2, 4i over n but squared, plus 4i over n and plus 4. Any questions? If you don't stop me, I will continue. So please stop me if you have anything for me. Okay, so then we continue. Have to simplify this. So this is 4 squared, which is 16 multiplied by 2, 32i squared over n squared, plus 4i over n and plus 4. I have all three preps. And now I know the area equals the limit as n approaches infinity from the sum from I equals 1 through n, delta x, 4 over n multiplied by f of xi, parentheses, 32i squared over n squared plus 4i over n and plus 4. The moment I calculate the sum and the limit, I'm done. I have the exact area. So let's continue. I'm applying one of the properties of the summation notation. If there is a factor that does not depend on I, I'll put it in front. That's my first step. Limit as n approaches infinity of 4 over n. I'm applying directly the next property, which is the sum of ai plus bi plus ci is the sum of ai plus the sum of bi plus the sum of ci. So brackets, the sum of 32i squared over n squared from I equals 1 through n, plus the sum from 4i over n from I equals 1 through n, plus the last sum of 4 from I equals 1 through n. At this point, I go back and use the same property again. Which property? The one with a constant. This is a constant. It will go in front. It does not depend on I. This is a constant. it will go in front. It does not depend on I. And this is 4 times 1. It's a constant. It will go in front. It does not depend on I. Now, I'm sure you understand what I'm doing because I know the summation of I squared, what it is equal to. We already proved it a few minutes ago. I know the sum of I know what that equals to, and I know the sum of 1, I know what that equals to. So the summation notation will disappear in a minute. So this is limit as n approaches infinity, 4 over n. This is 32 over n squared, and the remainder is summation of I squared. Well, I know what that is, n plus 1, 2n plus 1 divided by 6. Proved a few minutes ago, plus. Put in front 4 over n, and I know the sum of I is n plus 1 divided by 2. Plus, I put 4 in front, and the summation of 1 is n. Far from over, but much cleaner. All the summation notations are gone. I replaced them with identities. It's a long procedure, as you see. Okay, so this is the limit as n approaches infinity. 4 over n can wait patiently. Let's see what we can do. If I simplify by 2, it's not going to make any difference because then I still have to multiply this by 3 and this by 6. So I'm not going to worry about simplifying by 2. But I will simplify an n from the top with an n from the bottom, and I have left an n here. I will not simplify the n's here because the denominator will be 6n anyway. So I know that this will be multiplied by a 3 because 2n and then 6n is the least common denominator, and this by 6n. So n is the least common denominator. I have to distribute 32. I would like to distribute here. So I have 2n squared plus 3n plus 1, just to simplify my calculations. I distribute 32. 32 times 2, 64n squared plus 32 times 3, 96n. 32 times 1 plus 32 plus 12 n squared plus 12n and plus 24n squared. Any questions? Okay. Now I can simplify a little bit. So limit as n approaches infinity. The denominator is 3n squared. And let's see what we have at the top. 64 plus 24. That is 88. 88 plus 12 is 100. Don't forget about the 2. I was talking to myself, not to you. Okay. One more time. So this is indeed 88. 100, yes. 96 plus 12, right, is 108. N and plus 32. I want to put 2/3 in front and then limit n approaches infinity. The top is 100n squared. The bottom is n squared. Infinity over infinity, I will go ahead and differentiate. So I have 200n plus 108 divided by 2n. Again, it's infinity over infinity, L'Hopital's rule, and I have 200 over 2. So 2/3 times 200 over 2, which is 100. So this is 200 divided by 3. And this is the technique we need to use when we try to determine, or we want to determine the limit of the Riemann sum to determine the exact area under a graph. Any questions? And I know what's on your mind. Why we need to do this? It's for the same reason we determined a derivative initially with the limit of the difference quotient. And then we looked at differentiation rules. But we needed to understand that the derivative is a limit of the difference quotient. And then we looked at differentiation rules. Same thing here. First, we look at the limit of the Riemann sum, which is basically this in this analogy. And then we look at integration. Or rules of integration, if you want, or integrals. That's where they come into play, but specifically definite. We have two different types of integrals. Definite integrals. Okay. Not sure if you were paying attention. Do you want to move on? Do you want to look at another example? What would you like to do?
Can we look at another example?
Sure. Why don't we just look at the initial example that we had, where it's x squared and 0, 2. We looked at two subintervals, leftmost point, rightmost point, blah, blah, blah. And now we want to determine the exact area, because we can now with the limit of the Riemann sum. So the area is the limit as n approaches infinity from the summation from I equals 1 through n from delta x multiplied by f of xi. I need three preps. Prep number 1 is delta x, which is 2 minus 0 divided by n. Prep number 2 is xi, which was always going to be 0 plus, or the initial value, whatever that is. It's 0 here, that's why I put 0, plus I delta x, plus I delta x, so that will be 2I over n. And the third prep is f of xi. I need to have all these prepared before I put them in, because otherwise there is going to be no end to the calculations. So, nice. 2I over n, everything squared, 4I squared over n squared. Now I have all the preps, plug them in. So the area, limit, as n approaches infinity, from the sum from I equals 1 through n, from delta x, which is 2 over n, multiplied by the height, which is 4I squared over n squared. Couldn't be easier. This constant goes in front. Furthermore, you can say, because you don't have anything else, you can say I can use this and put it in front. That's even better. Limit as n approaches infinity. So this is 8 divided by n cubed. And this is the sum of I squared. And again, I know the sum of I squared is the identity that we chose to prove a few minutes ago. So that equals limit as n approaches infinity, 8 over n cubed, n plus 1, 2n plus 1 divided by 6. Yes, I'll simplify by 2. I'll simplify by n. And we have limit as n approaches infinity. 4 over 3 can go outside. Just 1 second, did I copy? I just wanted to make sure I copied the 2/3. Yes, I did copy it. For one second I said, oh, what if I forgot? Okay, no, I didn't. So 4/3 is outside. This is, again, 2n squared plus 3n plus 1. And So 4 is outside, so then we have n squared. When we apply L'Hopital's rule, we already know the answer here will be 2, but that's, let's say we don't know. So this is limit of 4n plus 3 over 2n. So 4/3 limit, differentiate again because it's infinity over infinity, 4 divided by 2. When n approaches infinity, we know that this is 2. So the correct answer, the exact answer is 8/3. And a long time ago, and I did not keep my papers in order because I went back and I didn't put them back. So where did we write that? I think we got 2.5 with the midpoint with 2 subintervals. I'll find it. Yep. So one was an overestimate, one was an underestimate, and here it is. We got 2.5 with only 2 subintervals, and a divided by 3 is 2.666. So even with 2 for different functions, even with 2 subintervals, we were quite close. Quite close. However, the area equals the limit of the Riemann sum f of xi is the same with